Topic of my paper is structural shape estimation by mode shapes using fiber Bragg grating sensors. And a genetic algorithm we will be using for the optimization of the sensor locations. So main objective of this paper is to estimate the shape of a structure using strain sensors, and the fiber Bragg grating sensors are used. Why? Because it is very small and lightweight, and there are some advantages. We will be discussing that. And another objective of this paper is to minimize the number of strain sensors, because sensors are costly. So we need to minimize the number of sensors, and for that we will be using an optimization algorithm, and a genetic algorithm is used in this paper. And why is we need to measure the shape? Because there are various applications, from the aircraft wing shape to the satellite, windmills, robotics, and medical fields. There are various fields. The shape sensing is very important. And in our work, mainly we are concentrating in the aircraft, because basically I am from the one organization, HAL, Hindustan Aeronautics Limited, and our motive is to measure the shape of the aircraft wing. We are using fiber Bragg grating sensor. Morning 2 talks were there related to the FBG, so I'm just fastly I will cover that. So when a broadband signal incident into a fiber Bragg grating sensor, on a particular wavelength called Bragg wavelength will reflect back. And this Bragg wavelength lambda b, which is dependent on the pitch of the grating and the effective refractive index of the fiber. And how we are, and the rest of the signal will be transmitted back, and that is we will not be monitoring. Only the reflected signal will be we are interested, and the peak of the particular reflected signal we will be monitoring. One of the main advantage of FBG sensor is like since we are detecting the peak of the signal, we can have, if the wavelength is different, using a different pitch in the sensor, then we can have n number of sensors along a single fiber strand. And this is very advantageous in case of in application like a shape sensing, because we need to use so many sensors. So we can avoid so many wires. Another advantage is like it is very it is small size, lightweight, and since it is immune to electromagnetic interference. And this is the fabrication facility at Indian Institute of Science. We are fabricating FBG sensors. We are using the Braggstar krypton fluoro XML laser with the 248 nanometer UV laser. And face mask technique we are using for fabricating the FBG sensors. And for each FBG sensor, we will be using different for each pitch. I mean, different pitch. We will be using different face mask. And in this slide, we are showing the sensitivity, how the sensor works. Basically, suppose the unstrained fiber with a particular pitch, which gives a lambda 0 wavelength, and if there is a compressive strain, then there will be a blue shift, and if there is a tensile strain, there will be a red shift. And the slope of this, the graph shows there other side, which gives a slope of 1.22 picometer per microstrain. And but this sensor is sensitive to temperature also. Here we can see that if the temperature decreases, again blue shift is there. If the temperature increases, red shift is there. But the slope is very high. It is 10 picometer per degree Celsius. So we need to compensate. Suppose we are using application for an application where both strain and temperature comes, we need to compensate that. There are the various techniques used. Like using one reference sensor, like that. There are many techniques are available. This particular work actually we are concentrating in the shape estimation part. how we shape estimation using model approach. Suppose we have a structure, we need to estimate the shape when it is in under operation. What we will do is like we will make the finite element model of that particular structure called the simulation model in this case, and we will do model analysis of that one, and using model analysis we will make one matrix called the strain to displacement transformation matrix. And in this matrix we will be using only few senses, few strain. We can see here only n sensor locations will in fact actually why we are selecting, because we don't want to use so many strain sensors. If structure in a structure, if you are using so many sensors everywhere sensor, then easily we can make the measure the shape of the structure. But we don't want to do that. Our requirement is to reduce the number of strain sensors. Then in the simulation itself we will do the static and transient analysis, and using these we will calculate the displacement, and we will estimate how much is the error for a particular set of sensor locations. And if the error is more, we will again select another location, but for that further slides will be explaining how. Now once we finalize the sensor locations, we will paste the really FBG sensors on that particular locations, and using the same strain to displacement transformation matrix, we'll measure the displacement, and this measured displacement will be compared with the calculated displacement will be compared with the measured displacement. And suppose there is difference between the simulation and the experiment, again we will rerun this one. So this is the iterative process till we get a satisfactory result. So come to the displacement calculation. So basically if you do the model analysis, we will get this type of matrix where capital M shows the number of measurements and capital N is the number of sensors selected and N is the mode shapes. And using least square approximation, there are so many equations, but ultimately what we will get is actually this is a matrix and this is the measurement, the real measurement from the FBG. And if you multiply this one, we will get the displacement. And in our particular this paper, we have selected one aluminum plate with 700 mm by 700 mm size and 2.5 mm thickness, and these are the material characteristics of this one. The first four mode shapes of this aluminum plate we show. And in this plate actually we fixed one end like a cantilever and we excited. So these are the first four mode shapes. And in the sensor optimization, what we are using is for optimization purpose, we will be using, we will estimating the error. The RMS error is calculated like this, where dA is the actual and DC is the calculated displacement. The genetic algorithm is used for the sensor optimization. What is coming to the genetic algorithm? In genetic algorithm, there is a initial population. Initial population means initial randomly we will select some number of places, sensor places, and we will calculate the RMS error for that particular locations. If the RMS error is within our acceptable range, then well and good, it is we will take that particular location. If not, then we will mutate. Mutate means we will select some other locations till we get a satisfactory level. So this is basically the simplest the genetic algorithm. So when we run this simulation in a loop, so this genetic algorithm in a loop, we can see that the RMS error is reducing gradually, and it will saturate at a particular value. And in this work, we selected some locations, and this cross is showing the sensor locations, and dots are the displacement measurement locations. In transient analysis case, one more observation what we have seen actually is uh, at resonant frequencies, the error is less compared to the off resonant frequencies. We have done a static experiment. Total 32 FBG sensors we used, and at 16 sensors, because we need X and Y strains, so 32 FBG sensors we used, and micron optics SM130 we used for with a 1 picometer resolution is there. And the displacement, we displaced the this particular plate in symmetrical and unsymmetrical in various shapes we displaced, and we tried to recreate the shape. And these are the static experiment results. It shows quite well. Actually, it given less than 0.5% error, because it is static case. Static case, it was much easier, but dynamic, it was slightly different story. In dynamic experiment, what we have done is like we with a model shaker we excited the same plate, and at different frequencies and amplitude. The displacement, because here it is, since the dynamic we used a non-contact type displacement sensor from micro epsilon. And these are the results. Dynamic shape, actually we can see that these two results shown here. One is at 4.3 hertz. 4.3 hertz is the first resonant frequency of that particular plate selected, and it is, the shape is estimating very well actually. But off resonant cases, there is overshoot in the edges. And these are the results at various frequencies. And here one observation what we are seeing is, as the frequency increases, the error is also increasing. But in most of the application, especially in our application, where we need to measure the shape of the wing, aircraft wing, so we are interested in less than 10 hertz. So it is quite well for our application. But again, it depends on the application to application, it varies. Conclusion. So shape estimated using model approach, and FBG sensors are optimized, sensor locations are optimized using genetic algorithm, and shape estimation error was less than 0.5% for static cases, and dynamic cases at resonant frequencies it was quite well compared to the off resonance frequencies. And thank you.